One of the most important things that you need to understand is where can the closed loop poles lie in the complex plane. Now, the basic requirement is for the system to be stable. So you can't have roots in the right half plane, but you can have roots in anywhere in the left half plane. So if you don't have any other constraints, then the whole left half plane is the place where you can put your roots anywhere here for the control system, complete control system. So closed loop poles can lie anywhere here in the left half plane. What happens is as you put constraints or time domain specifications, you carve out regions of this left half plane as invalid. For example, so let's say our rise time, we say, which is equal to 1.8 divided by omega n is less than 0.2 seconds, which means that omega n should be greater than 9. So you can't have roots inside a circle of radius 9. So the only valid region is whatever is left on the outside. Let's say in addition to that I have peak time should be less than 2 seconds. That gives me this condition that my damped natural frequency should be greater than 1.57. What does that mean? That means so damped natural frequency is the distance from the real axis. So you draw a line omega d equal to 1.57 and nothing can lie inside this band. Now again carved out this region, so the only valid region is this blue region that's left here. If you put another constraint, percentage overshoot is less than 10%. That corresponds to a zeta value of zero point 0.6, which is 36.8 degrees, which means you carve out again. Things have to be outside this uh, triangle. So again you carve out. So the only valid region is what is left. So that's how that's what your time domain specifications do. They carve out your left half complex plane and leave you with a valid region where you can do pole placement or choose to put your closed loop poles. So in essence, controller design is nothing but pole placement of the closed loop transfer function. So we'll go into more detail when we do root locus what this pole placement means. Now let's do a first problem. Let's design a controller. So we have this configuration here. This is a proportional rate controller. So why is it rate? Because you take the output, multiply it with s, that gives you differentiation, that gives you the rate, and feed it back like so. Now the first step here is to find the generic transfer function. Let's see what the time domain specifications. I have two specifications. 4% settling time is less than 2 seconds and peak time is less than 0.2 seconds. Those are my two specifications. Now the first step is to find a closed loop transfer function. So you do block diagram manipulation and then find the closed loop transfer function like so. We substitute GP and we find the actual transfer function as 2k divided by s squared plus 2 plus kd times s plus 2k. Now this is second order system without zeros. So you make an identification with second order parameters like so, and you know that omega squared equal to omega n squared equal to 2k. That's right here. So omega n is root of 2k. 2 plus kd is 2 zeta omega n. 2 plus kd is equal to 2 zeta omega n. So zeta from this and this will give you 2 plus kd divided by 2 root 2k. And kdc times omega n squared equal to 2k, and therefore kdc equal to 1. Now we put in design specs. So we have the two relationships, omega n squared equal to 2k, which gives you omega n equal to root 2k, 2 plus kd equal to 2 zeta omega n, which gives you zeta equal to 2 plus kd divided by 2 root 2k. So first design spec, say settling time is less than 2 seconds, 4% settling time is less than 2 seconds. So 4.2 divided by zeta omega n is less than 2. and then we substitute the value of uh, zeta times omega n. That is from here, zeta times omega n is 2 plus kd divided by 2. So 2 plus kd divided by, that is less than 2. So kd should be greater than 2.2. That's one constraint. That's a constraint on kd. So as long as kd is greater than 2.2, we satisfy the settling time. Now let's look at the second constraint, which is peak time should be less than 0.2 seconds. So pi divided by omega d is less than 0.2 seconds. So we'll find out what omega d is, which is omega n times root of 1 minus zeta squared less than 0.2 seconds. So omega n squared, I've squared this up and moved terms around. So omega n squared times 1 minus zeta squared is greater than 25 pi squared. Then I substitute for omega n squared and 1 minus zeta squared from here. So this equation is greater than 25 times pi squared. I multiply throughout by the common denominator and bring this to this side, and I get this equation 16k squared minus 16k minus times 2 plus kd the whole squared minus 25 pi squared times k is greater than 0. So that gives me k times 16k minus 16 times 2 plus kd the whole squared minus 25 pi squared is greater than equal to greater than 0. So this condition is only valid if either k is less than 0 or this whole term is greater than 0. K cannot be less than 0, because if k is less than 0, then your omega n becomes complex. You can't have complex natural frequency. So naturally we say that k is, this term is greater than 0. If this term is greater than 0, then this equation becomes valid. So what does this mean? So one, you have to have kd greater than 2.2. The other says that k should be greater than 16 times 2 plus kd the whole squared plus 25 pi squared divided by 60. So you can choose any value of kd greater than 2.2 and then find out what's the minimum value of k that you require to satisfy peak time constraints. Now if you plot this on a kd-k plot, so you have kd on the x-axis, k on the y-axis, this is how it will look. So I have kd here like so and k here. Kd should be greater than 2.2, and this constraint is given by everything that's above this curve. This curve is k equal to 16 times 2 plus kd the whole squared plus 25 pi squared divided by 16. So you can choose any value of k and kd in this region, and both constraints will be satisfied. That's the end of our lecture.